For the do now today, we have questions that go back to the first and second video or some questions from yesterday. And then I want to focus on a question similar to what we did yesterday, but how KA can be represented a little bit differently. Because College Board has started to ask more questions where they're representing KA a little bit differently. And so I want to make sure that we focus on that as well. So for number 1, calculate the pH and OH minus concentration of a solution with an H plus concentration of 5.55 times 10 to the negative second molar. Is this acidic or basic? And justify your answer. So they already gave us H plus. They didn't tell us anything about an acid or a base or anything in equilibrium. They just gave us the H plus concentration. We're going to use the H plus concentration to find each of these variables. If you're like, well, I don't really remember how to calculate pH or OH minus concentration, look at your equation sheet. Because on your equation sheet, you have pH equals negative log of H plus. So we know that pH equals negative log of H plus. Since we have the H plus concentration, we can just plug it in. So negative log of 5.55 times 10 to the negative second molar. So in my calculator, negative log of 5.55 e negative 2. 1, what's that, 3 sig fig, so 3 decimal places, 1.256. And I know that I put pH equals all the way over here, but just to make it easier when your question is being graded, just go ahead and do equals pH. Make it easy to find, easy to figure out what it is. The second thing that it wants us to calculate is the OH minus concentration. So there are 2 ways that you could find the OH minus concentration. One way, it takes a couple extra steps. The way that I'm going to do it is I'm going to remember that OH minus and H plus are related through KW. Again, on your equation sheet, you have KW equals H plus times OH minus concentration. So KW is 1 times 10 to the negative 14. Because unless it specifies, or unless it says otherwise, we assume we're at 25 degrees Celsius. So KW equals H plus concentration times the OH minus concentration. So we can solve for OH minus. 1 e negative 14 divided by 5.55 e negative 2. The OH minus concentration, 1.801, nope, 1.802 times 10 to the negative 13. Remember that brackets means molarity, so we need to make sure to include a unit. Now, another way that you could have done this is you could have used the pH to find the pOH, and then use the inverse log to find OH minus. You would still get the same thing. Rounding might be a little bit different, but it should be close. Now, the last part of this asks, is this acidic or basic, and justify your answer. Remember, if it says justify your answer, provide some sort of reasoning. So there are 2 ways that we could figure out if this is acidic or basic. One way is to look at the pH. It's a low pH. Low pH means that it's acidic. So I know that this is acidic. Now the other way that we could justify our answer is comparing H plus concentration to OH minus concentration. There was the table in video 2 on comparing H plus to OH minus. If you compare these numbers, H plus is greater. -2 compared to -13. Since H plus is greater, H plus identifies an acid. OH minus identifies a base. So for my justification, I'm actually going to say H plus concentration is greater than OH minus concentration. You also could say pH is less than 7, or there's a low pH that tells us that it's acidic. I'm going to relate it back to H plus and OH minus. So again, that goes back to the second video, so back to last week's material. Number 2, when NaCN is placed in water, what is the pH? And I said just give the range. So NaCN, you always want to get in the habit when you have a substance of identifying it as an acid, as a base, or as a salt. If we look at number 2, NaCN, well, I noticed that there's Na at the beginning. That's a metal. That's a cation. NaCN is actually identified as a salt. It's 2 ions, a cation and an anion, put together. Because this is a salt, we need to figure out how each part of the salt affects the pH. So remember yesterday we looked at how different parts of the salt affect the pH, and it's based on the cation and the anion. The cation of the salt always comes from a base, so that means that Na plus comes from NaOH. The anion comes from an acid. Cn minus is the conjugate base of HCN. And so based on the acid and the base that these ions come from, we can figure out how the salt affects the pH. NaOH is a strong base. If NaOH is a strong base, that means that Na plus is a neutral cation. Because remember, you have one of 2 pairs, strong neutral or weak weak. HCN, that's an acid, it starts with an H, but it's not one of the 7 strong acids. HCN is not one of the 7 strong acids, so it's a weak acid. If HCN is a weak acid, that means that Cn minus is a weak conjugate base. Now, labeling these ions helps us see how each affects the pH. Na plus is neutral. Neutral will not affect the pH. A neutral substance like Na plus will not affect the pH. It's not going to do anything to it. Cn minus, though, we said is a weak base. A weak base is still a base. So Cn minus is going to make this pH basic. So we have part of it that's not going to do anything. Part of it's going to make it basic. So overall, we would expect this pH to be basic. Now it said to give the range of pH. Well, if it's basic, we expect the pH to be above 7. Where above 7, we don't know. But we know that this is going to be a basic salt. Na plus is neutral. Not going to affect the pH. Cn minus is a conjugate base of a weak acid, so Cn minus is weak base. So the pH we expect to be somewhere above 7. Now number 3 says write the equilibrium equation when the salt from number 2 reacts with water. And I said only focus on the part of the salt that affects pH. So we just said the only part of the salt that affects pH is Cn minus. Nothing else, right? Na plus is neutral. It's not going to affect the pH. So number 3 wants me to show Cn minus at equilibrium when it reacts with water. Now I know it's at equilibrium. It told me it's an equilibrium equation, but I also know it's at equilibrium because this is not strong. Now we've already identified Cn minus as a base. So we've actually already identified Cn minus as a base, but even if we didn't, Cn minus cannot act as an acid. Because in order for Cn minus to be an acid, it would need an H plus to donate. Cn minus doesn't have an H, so it can only act as a base. So what that means is water is going to act as the acid, donating one of its H pluses to Cn minus. Cn minus will become HCN. Remember, all acids are aqueous. And once water donates its H plus, it becomes OH minus, and ions are also aqueous. This is why Cn minus makes a salt basic. A salt is always dissolved in water because of the products of an acid-base reaction. When Cn minus is in water, it produces OH minus. If it produces hydroxide, it's a base. So that's why Cn minus makes the pH basic. That's why Cn minus acts as a weak base. The rest of number 3 says write the Kb expression. Now we're going to do more with Kb today when we look at example 18. The difference between Ka and Kb is solely that B means base. B means that our equilibrium that we're focusing on should be producing OH minus. That's the only difference. Ka is producing H plus or H3O plus because it's focusing on an acid. Kb means we're focusing on a base. Kb expressions are written just like Ka, just like Kc, just like Kp. Products over reactants, you ignore solids and liquids. So the Kb expression is the concentration of HCN times the concentration of OH minus over the concentration of Cn minus. Again, it's Kb because it's producing hydroxide. And then finally, number 4, and this is kind of the most important part. If the pKa, notice that P in front. If the pKa for HA, so some acid, is 3.097 at 25 degrees Celsius, what percent of the acid is ionized in a 0.5 molar solution of HA at 25 degrees Celsius? So I'm going to erase this part of the do now. I'm going to do the work up here. So there's one thing, I put it at the very top of the screen. From page 7 of your notes. On page 7 of your notes, you had this equation right here. pKa equals negative log of Ka. You also have that as the very last line of equilibrium on your equation sheet. College Board likes representing Ka values as pKa. It's just a shortened version of Ka. So if they give you pKa, P just means you've taken the negative log. pH means you've taken the negative log of H. POH means you've taken the negative log of OH. pKa means you've taken the negative log of Ka. So if they give you the pKa value, they actually have given you Ka. So in this case, right, I'm gonna answer the question in this blank space up here. So they actually gave us Ka. Let's figure out what the Ka is. So if the pKa is 3.097, think about how you go backwards from pH to H+. You need to take the inverse log. Ka is 10 to the negative pKa. Just like if we have H+ from pH. So the Ka value of this acid is 10 to the negative 3.097. What is that? Free sig fix. 8.00 times 10 to the negative 4th. There's our Ka. There's our Ka of our weak acid. The reason I know this is a weak acid is because remember that strong acids dissociate completely. They're not going to have a Ka. Or if they do, it's like upwards of, 1,000,000. So there's our Ka. Now the rest of this is actually asking about percent ionization. So here's what I'm going to do. I'm going to write the acid equilibrium. So just like we've been looking at, I'm going to write the acid equilibrium expression or equation. HA just means it's some weak acid. It's at equilibrium with H plus and A minus. Now, in the problem, I'm just going to fill in information that I know. It tells me that we have a 0.50 molar solution of HA. And it's asking what percent of the acid is ionized. It's asking for percent ionization. We remember from yesterday, percent ionization is H plus concentration at equilibrium over initial concentration of the acid times 100. That is not on the equation sheet, but I guarantee you will see a question with percent ionization on the test. They ask one almost every year on the AP test, so I always make sure to put one on the test. H plus at equilibrium over HA, right, the initial concentration of the acid. The point of percent ionization is to see how much do you have at equilibrium versus how much did you start with. So since I have a weak acid, I'm going to go ahead and set up an ice table. Because to solve for percent ionization, I have the initial concentration of the acid, but I also need to know how much H plus do I have at equilibrium. Unless it says that you have something else initially, H plus and A minus are 0. Now I don't have anything else. I have Ka and that's it. So I'm going to use x's. Minus x, plus x, plus x. So there's our equilibrium row. So now we have our equilibrium row, and we have our equilibrium constant. We have our Ka. I'm going to just come right down here. So Ka is H plus concentration times A minus concentration over HA. If you're using an equilibrium constant, you need to use equilibrium concentrations. So 8 times 10 to the negative 4th is x squared, or 0.5 minus x. I'm going to make the note up here. Assume x is small. We assume x is so small, it's not going to affect that 0.5. So 8e negative 4 times 0.5. Take the square root. Oh, we technically could have done this without a calculator, but that's okay. X is 0.02. After you solve for x, take just a second and look at what the problem wanted you to solve for and why x would be useful. Because I see that I underlined H plus at equilibrium. That's 0.02, 0.02 molar. So now I have H plus at equilibrium 0.02 molar. I always have the initial concentration of the acid, 0.50 molar. I'm going to multiply by 100. 0.02 divided by 0.5 times 100. This is actually a fairly strong weak acid. It's not a strong acid, but the example yesterday, if you remember, we calculated the percent ionization to be 0.69%. This is 4%. So that means if you have 100 molecules of this weak acid, 4 of them, right, 4 of the 100 will break apart into H plus and A minus. The other 96 will stay together. So I know that this took a little bit longer than normal with the PA or with the do now, but I wanted to make sure that we got some of the older calculations. We looked at some things from yesterday, and I really wanted to hit on pKa and how that can represent Ka, while also doing another example like yesterday. Any questions on the do now? All right, so then we will get into examples. So today we have the last 2 from 7.3, so we finally get to finish those up. And then we have the 2 from video 7.5. And I'm going to try to give you some strategies, tips, tricks with video 7.5. I'll show you very common types of questions that you see with 7.5. And then hopefully you'll have some time to work on mastering. So for example 17, you flip in your notes to example 17. It looks like this. It says citric acid, which is present in citrus fruits, is what's called a triprotic acid. Tri means 3, protic for proton. Triprotic has 3 protons, 3 H's. It says calculate the pH of a 0.050 molar solution of citric acid. And you see that you have 3 equilibrium equations here. If you actually look at Appendix D, right, in Appendix D, citric acid has 3 Ka values. And if you look at citric acid, it has 3 Ka values. The 3 Ka values represent each H that's being removed. So Ka1 represents the first H being removed. Ka2 represents the second H being removed. Ka3 represents the third being removed. When we have a polyprotic acid, whether it's diprotic or triprotic, we typically just assume that the first ionization is the most important. And you have this statement already written in your notes. Right? In your notes, it already says to calculate the pH, assume initially that only the first ionization is important. Typically, the first Ka is the largest Ka. That's the one that's most likely to occur. So we're only going to focus on the first Ka. We're only going to focus on the first ionization, the first H plus being removed. But I do want to point out how only one gets removed at a time. It's not going from H3, C6H5O7, to C6H5O7 at once. You have one H that's being removed at a time. So what I want you to do is write the acid equilibrium equation for the first ionization. So it's just this first ionization equation we're just rewriting. The reason that we're rewriting it is because it's a weak acid. We have to do any calculations with a weak acid. We're going to need an ice table. Now, if you ever look at any of the College Board like practice videos that they put up, or other teachers, like if you find other teachers' explanations on YouTube, sometimes instead of ice tables, you'll hear them say rice tables. Well, we actually do that already because the R means reaction. So when we make our ice tables, we make them like this with our reaction at the top. Some people call them rice to make sure that you put the reaction. So just in case you ever are looking at anything and you hear them say rice, it just means reaction. So our goal is to calculate the pH. Our goal is to calculate the pH of this weak acid. Now, because it's an acid, I'm going to look at the equation, and I remember that pH is negative log of H plus. pH is negative log of the concentration of H plus. But the pH uses H plus at equilibrium. So I actually need to solve for this spot in the ice table. So then we plug in what we know. Even if you can fill in the ice table, it's a very good strategy to always use an ice table. 0.05 molar, 0, and 0. They didn't give us anything else. They didn't give us pH, which tells us H plus at equilibrium. They didn't give us anything else to plug into the ice table, so we need X's. So the acid is going to decrease by X amount. H plus and H2C6H5O7 minus both increase by plus X. Remember, the change row is based on the stoichiometry. They're all 1 to 1 to 1. So we get 0.05 minus X, X, and X. Now you get to this part, and it's important to think about, okay, well, I have these variables at equilibrium. What can I use if I have equilibrium? Well, we have our Ka. We are only assuming that the first ionization is important, so we're using the Ka that goes with this equation. So if I write the Ka expression off to the side, H plus times H2C6H5O7 minus over citric acid. Now we plug in what we know. This is an equilibrium constant. We need equilibrium concentration. So Ka for the first ionization, 7.4 times 10 to the negative fourth, X squared over 0.05 minus X. If you're making the assumption, make sure to write it down somewhere. Assume X is small. Because we assume then that that minus X does not play a role in changing the initial concentration of the acid. 5 square root. I get my X value, 0.006, two same things, 0061. There's X. Now I'm going to pause and I'm going to say, okay, what is X? Why is X important? Well, X is 0.0061. That's the H plus concentration. That's the anion concentration. And I look back and say, okay, I need pH. pH is negative log of H plus. Negative log of 0.0061. So negative log 0.0061. And the pH is 2.21. Now, I'm going to just look at that. Citric acid is a weak acid. We were focusing on Ka values, so it makes sense that we have a pH of 2.21. So this is just like what we've been looking at before. We looked at calculating pH a couple days ago, but the difference here is that we had a polyprotic acid. In this case, it was triprotic. when you have an acid with multiple protons, we are going to always assume that only the first ionization is important, right? Just the first ionization. Any questions on this one? But I think the bell's going to ring in just a second. Oh, yeah.
How do you know to use the first equation?
So just when we look at polyprotic acids, we're always just assuming that the first one, because the first one is usually the largest Ka, we're usually going to use the largest value of Ka.
Oh.
So whichever Ka is the largest, that means that that's the ionization that happens most often. And so that's the ionization that we're going to use. Typically, it's almost always the first one, which is why we use that. This example 18, is actually like numbers 31 and 32 on mastering. So if you want to make yourself a note, 31 and 32 on mastering. This is looking at a weak base. So in this example, it says calculate the molar concentration of OH minus ions. So my answer needs to be OH minus ions and a 0.050 molar solution of hydrazine. Now, one way to know that this is a weak base is that when you have substances that have NH2, so when you have this NH2 group at the end, that's called an amine, A-M-I-N-E. It's an organic functional group. But amines are bases. They're weak bases. Now, the other reason that I know this is a weak base is because they gave me the Kb value. Kb means we're dealing with a weak base. And then it also asks for the pH. Now, it's important to remember if we're dealing with a base, pay attention to what we're calculating. So the first thing that we need to do is we need to write the equilibrium equation like we do with acids. Now with bases, we need to make sure to include water. And the reason that we need to make sure to include water is because bases need to accept a proton. So I think it was your question yesterday on whether you need to include water or not. With acids, it's up to you on if you want to do plus H2O. If you do plus H2O, then instead of H plus, you're going to have H3O plus, right? And that means the same thing. With bases, you want to include H2O because that's where you're getting the proton from. If this is a base, water has to be the acid. And so it's actually going to accept a proton. Once hydrazine accepts a proton, it's going to become H2N NH3 plus. Now, if you did H3 and NH2 plus, I would accept it. Mastering, if you're doing a question like that on mastering gets a little finicky because it wants you to put the plus right next to where the positive charge is. The positive charge is located where there's 3 H's, so that's why we write it like we do for bases. And then once water loses the proton, it becomes OH minus. So notice why hydrazine is a weak base. Because when it's with water, it produces OH minus in solution. So because we're dealing with something that's weak, we're going to need an ice table. Whether it's a weak acid or a weak base, we need an ice table. Now, here's what I want to make sure that we do. We need to focus on what the question wants. Once I set up the ice table like this, I'm going to go back and look at the question and say, okay, what does it want me to find? Well, one of the things is the concentration of OH minus. If it's asking me for concentration of OH minus, it wants OH minus at equilibrium. But it also wants pH. Now, I just want us to think really quick before we have numbers here. If I take the negative log of the OH minus concentration, what am I finding?
pOH.
pOH. When I take the negative log of the OH at equilibrium, that's POH. It wants me to find pH. So how do I find pH from that? Right, 14 minus POH. And if you're like, well, I don't know, I don't remember. Take a look at your equation sheet. It has 14 equals pH plus POH. So I just wanted to write that down initially so when we have numbers, we're remembering what we're finding. So let's look at what we have. So we have a 0.05 molar solution of weak base. I'm going to put an X through H2O. Why can I put an X through H2O? It's a liquid, right? Liquids do not affect equilibrium. And then, because it doesn't say anything else about initial, they're 0. Now, it doesn't say anything else. So I'm going to use X's. Plus X. Plus X. Now, because this is a base, we're using the KB expression. And so that is our conjugate acid, H2N, NH3 plus, times OH minus, over H2N, NH2. No water. This water's a liquid. So now they gave us the KB value, 1.3 times 10 to the negative 6 is X times X over 0.05 minus X. Again, if you make the assumption, you have to write down that you're making the assumption that X is small. You know, don't simplify, assume, because there are some great stories about when people assume X is small and they try to shorten assume. So when we assume X is small, minus X gets ignored. So 1.3 e negative 6 times 0.05. You get 6.5 times 10 to the negative 8. You take the square root of that to solve for X. 2 sig big, so 2.5 times 10 to the negative 4. I notice that I underlined the X over here. 2.5 times 10 to the negative 4 is the molarity of OH minus. Now, I'm keeping it in my calculator, so you might round a little differently, which is fine. When I do the negative log of OH minus, we are finding POH. Here's where labeling becomes very important. Oh wait, 2 sig figs means 2 decimal places. So 3.59. This is where writing this has now become helpful because now I can just do 14 minus 3.59, 10.41. Now you can ask yourself, does it make sense that the pH is 10.41? Well, we're looking at a base. So yeah, it should make sense. It should make sense that the base has a pH of 10. Bases should be above 7. Now, I just want you to write this equation down. We're not going to actually do this calculation. But if we focus on percent ionization, I want to just look at how this is similar but a little bit different from an acid. Percent ionization means the same whether you're looking at an acid or a base. You're looking at how many ions do you have at equilibrium compared to the initial amount. So if we're looking at the percent ionization of a base, it's going to look just a little bit different because a base means we're focusing on OH minus. So if a question says what's the percent ionization of the base, we're going to compare the OH minus concentration at equilibrium to the initial concentration of the base times 100. So the percent ionization of a base is just slightly different because we're focusing on the OH minus concentrations at equilibrium compared to the initial of the base, where an acid was H plus at equilibrium compared to initial of the acid. And again, we're not going to actually calculate, but I just wanted to focus on that equation. Any? Yeah.
Why can't you take an H plus from the H2 and H2 and move it over to the H2?
So since they give us the Kb value, they're telling us that this is a base.
Okay.
Now, in terms of why this won't act as an acid, that has to do with the Lewis structure, with the electronegativity, with the strength of the bonds. But because they gave us Kb, they're telling us that it's a base, which means that water has to be the acid. Yeah. Any other questions on this? All right, so now we have two more examples, and these are conceptual. So these two examples are going to go along with the last video, so video 7.5. Now, example 21 isn't as common as example 22 will be when we look at acid strength. So when we look at acid strength, there are a couple things that we can look at. Example 21 is actually looking at transition metals or just metal cations and looking at which would be more acidic. So example 21 says predict which member of each pair produces the more acidic aqueous solution. So predict which in the pair, so we're just going to circle, produces the more acidic aqueous solution. So when we're comparing ions that are similar, metal ions, the more positive is the stronger acid. So the more positive is the stronger acid. And the reasoning has to do with the hydrated cations. We're not going to talk much about complex ions, but it ties into the complex ions. So we just need to know the more positive, the stronger the acid. So when we're looking at part A, which one has the more positive charge?
Copper.
Right, copper, Cu2 plus. Here's the one that's the most acidic. K plus is also neutral because it comes from a strong base. But if we're just focusing on positive, right, part B, we have Fe2 plus or Fe3 plus. Well, Fe3 plus has a higher charge. That's the one that's going to be more acidic. Now in part C, they have the same charge. So something to think about when they have the same charge. So if they have the same charge, the smaller ion is the stronger acid. So now we have to think back to sizes. So we look at the periodic table. We're comparing aluminum and gallium. They both are +3, so we can't use the positive. The tiebreaker is that the smaller, the more acidic it is. So aluminum has valence electrons in N equals 3. Gallium has valence electrons in N equals 4. Gallium has an extra energy level. Gallium is larger. All right, so since aluminum is smaller, it's the stronger acid. And that's it for example 21. Right, we just have to remember that the more positive, the stronger the acid, and the tiebreaker is if they have the same charge, and the smaller ion is the stronger acid. Now, example 22 is the one that you will. I will tell you, you will see questions like this on the test. All right, so when it comes time for the acid-base test, and even tomorrow on the quiz, right, you very well could see a question like this. So these say, explain the following observations. So they give us an observation, and we have to explain why it's true. We can't go against it and say, well, that's not true, right? They're telling us that this is what's true. So part A says HNO3 is a stronger acid than HNO2. So something that I just want you to keep in mind. All right, something I want you to keep in mind is that the easier the bond breaks, so we have hydrogen, like in this case, we have hydrogen bonded to something. Remember that a strong acid completely ionizes, it completely breaks apart. So the easier the bond breaks, the more ions in solution, and the stronger the acid. So when we're looking at explaining, we need to keep in mind that the easier the bond breaks, the more ions that exist in solution and the stronger the acid. So the video looked at different types of acids. It looked at oxyacids with different numbers of oxygens, with different central atoms, or binary acids. So if we look at part A, HNO3 is a stronger acid than HNO2. You need to look at how they're similar and how they're different. So I notice here that it's HNO3 versus HNO2. So this is actually comparing two oxyacids. Oxy means they have oxygen. But they have, one has 3 oxygens, one has 2 oxygens. So the reason that HNO3 is a stronger acid is that HNO3 has more oxygen atoms. Right, that's O for oxygen, not a 0. So HNO3 has more oxygen atoms. And there are more O atoms, the electron density shifts away from the H bond, right? Not a hydrogen bond itself, but the actual H in the bond. And it's easier to remove the hydrogen. Need to get a new marker. Guys online, I'll read this because I know it's hard to. So HNO3 has more oxygen atoms. When there are more oxygen atoms, what happens is that oxygens are pulling all of the electrons toward them, leaving the hydrogen kind of out on its own. It's still bonded, but oxygen is pulling all the electrons toward it, and it's easier to remove the H. Easier it is to remove the H, the stronger the acid. So HNO3 is a stronger acid. Be able to explain an oxyacid question like this. Right? Be able to explain an oxyacid question like this. So then B says H2S is a stronger acid than H2O. Well, these are binary acids. Hydrogen with just a single element. When you have a binary acid, compare where the two are. O and S are in the same group. So we'll say bond strength decreases down a group due to size. H is easier to remove from S because it's larger. So again, the easier it is to remove the H, the stronger the acid. Because sulfur is larger, the nucleus of sulfur cannot attract the hydrogen as much as the oxygen. So the bigger the atom, the harder it is for it to hold on to the oxygen and the easier, or the hydrogen, and the easier the hydrogen gets removed, the stronger the acid. Part C, H2SO4 is a stronger acid than HSO4 minus. So what I notice difference here is the charge. So the more positive, the stronger the acid. So since H2SO4 is more positive than HSO4 minus, it's a stronger acid. Part D, H2SO4 is a stronger acid than H2SeO4. So now here I notice that the central atom is different. When you have an oxyacid with a different central atom, you look at electronegativity. So S is more electronegative than Se. So S pulls electrons away from the hydrogen, and it's easier to remove. So kind of like with the oxyacid idea. Sulfur is more electronegative. Sulfur is pulling the electrons toward it more than selenium. And so since sulfur is pulling the electrons toward it more, hydrogen is easier to remove. And then we have CCl3COOH versus CH3. So here I notice the difference is Cl versus H. Again, the reasoning is like part D. Cl is more electronegative than H. Since Cl is more electronegative than H, it's pulling on the electrons more, so it's easier to remove the hydrogen.